Hello and welcome back. After finishing the discussion on the numeric sequences, we're going to get more into the functions, and it's better to start with the elementary functions. And the most important elementary functions are the exponential and the inverse of the exponentials, which is a logarithmic. So these are functions and inverse functions. So what is an exponential function? So exponential functions is usually given by a to the x is the variable here, and a is the some base, which is a constant, right? It's not the variable. Now, if you remember from basic algebra, if the base is the variable to some power, then we call it a polynomial function. But this is not what we're going to discuss. We're going to discuss power functions, and exponential function. So I want to make sure that you understand the difference between a polynomial when the base is the variable and an exponential or the power function where the exponent is the variable. Okay, so x is our exponent. All right, so first of all, the exponent could be any positive or negative number. We don't have any constraint on that. But the base has to be a positive number. I'm going to write it down. The base has to be a positive number. Now, why is that? Because we don't know how to define the result of having a negative number, let's say minus square root of 2, to an arbitrary power. If we raise minus square root of 2 to, let's say, 1.3 power, right? Let's call it a. We actually don't know how to define this. What is minus 1 to the 1 to 1.3 power? We don't know. Okay, but we do know how to define the power of a positive number to some arbitrary power. Okay, so the base has to be a positive number. Now, if the base is between 0 and 1, we already know that the higher the power is, the smaller it becomes, right? Because if you think of raising to some power as multiplication of the number a by itself, okay, then if a is between 0 and 1, each time you multiply it by itself, it just decreases. And on the contrary, if a is between 1 and infinity, is a number greater than 1, each time you multiply it by itself, it just increases, okay? So, in other words, if we look at these diagrams, let's look at the diagram on the right. This is for the case when is a, our base, is greater than 1. And the horizontal axis is x, our exponent, and the y is our function, or the result of the function, a to the x, right? If my x is a very large negative number, let's call it minus infinity, right? Then my function is very small, so this, we say that it asymptotically goes to 0. Asymptotically goes to 0. If x is 0, regardless of what a is, this is always 1. This function is always 1. So any positive number to raise to the power of 0 is always 1. This is the convention. And if a is greater than 1, we already discussed that if x is a great number, then we have to go to the result is a very large number. So this function, we call it monotonically increasing. It's a monotonic function, monotonically increasing. We'll get to this a special function e to the x. It's a very special number that appears in a lot of physics problems. That's why it's sometimes also called the natural number. it's an irrational number. Unlike, for example, 10 to the x. 10 is a rational number and 10 to the x is well defined. Now, on the other hand, if our base it is between 0 and 1, okay, then the function is monotonically decreasing. So it decreases. If x, our exponent, is a very large negative number, then the result, the function, is very large. If x is 0, by definition, the result should be 1. Any number to the power of 0 should be 1 again. And as x goes to a very large number, then our result should be very small. Okay? You should be able to justify why this behavior happens. And again, if you assume that the power raising some number to a power is just multiplying that number by itself, then it's very easy to justify this behavior. For example, 1 over 2 to the power of x. If x is 2, then 1 over 2 is 1 over 4, right? 1 over 2 to the power of 2. Therefore, it becomes smaller and smaller. Now, the inverse of the exponential function or the power function is called the logarithmic function. And just as we said that a is the base of our exponential and x is the power or the variable, the inverse is basically a function that you give it f of x or the result of the exponential and give it the base, and it returns to you the exponent x, right? So we said that first of all, a should be greater than 0. The base cannot be negative because we don't know what to do or how to define it if it's negative. And the exponential function always returns a positive value. It never returns a negative value. Again, because we don't know how to define it. Okay? So the inverse, when we define the inverse function, the domain and the range of the function, they just interchange. So the logarithmic function should take a variable x, which is between 0 to infinity, and then return some number. Some real number, could be positive or negative. And as I discussed this, the inverse function, basically you give it the base and some variable x, and it gives you a result y, such that if I take a and raise it to the result y, it should give me the input x. Okay? Now if we use the e as the base, again, e is the natural number, and then the log function, we usually don't specify the base. You don't write it down explicitly. Instead, we use ln, which is called the natural log function. Okay, so ln e to the x, these happen all over the physical problems. Any physics problem, these functions happen. So it's very good to understand them, understand their properties. And we will get to these functions in very details when we talk about the derivatives on functions, integrals, all this good stuff. Okay? Alright, so let's do a formal definition of logarithmic function. F of x is log of x to the base of a, right? Again, a is the base. It has to be a positive number. Base has to be positive. We don't know how to define if it's negative. And it can have two regions, between 0 and 1 or greater than 1. Okay? Now the domain of logarithmic, or the values, the valid inputs for the logarithmic function, should be positive, and the output can be anything positive or negative, right? Now if we put a positive number and a is between 0 and 1, we get a negative number. And if a is greater than 1, we put a positive number, we get a positive number. And let's have a look at the plot of logarithmic function. Now in order to find the plot, we first plot y of x, y equal x, and then we plot the exponential a to the x, assuming that a is greater than 1. Okay? And remember here, and then we just mirror it with respect to the uh, y equal x. So this is log of a of x when a is greater than 1. And again, if a is greater than 1, remember these two plots, when a is greater than 1, the exponential function is monotonically increasing, okay? Then if the input of the log is greater than 1, we get a positive number. If the input is less than 1, we get a negative number. Now let's look at the other way. Let's assume that fx and we plot y equal x. Let's assume that a between 0 and 1. Our base is between 0 and 1. And then we get this function, right? At x equals 0, it's 1. And if I mirror it, what do I get? I get something like yeah, we can mirror it and find what the result is. Again, at 1 it should be 1, so it should definitely pass through this point. X equal 1 and y equals 0 should pass through this, okay? And it should have a shape like this. Should have a shape like this, okay? So in this case, when x between 0 and 1, the function is positive. When x greater than 1, the function is negative. Exactly the opposite of the previous case, okay? Just a side note that when we're dealing with function f of x, especially these type of elementary functions, your ability to being able to quickly graph the plot of the function and put on the important values, for example, for the a to the x, at the point at x equals 0, the value of the function is always 1. So that's a very important point. So if you're able to draw the function quickly and put some important points, it can help you a lot in understanding the behavior of the functions. And we'll get to this in very more details when we talk about the derivatives and how to plot functions based on the slope of the tangent lines. We'll get to all of these. Just bear with me and repeat these as we go along, okay? Now, properties of the exponential and the log functions. If log of x in the base of a is y, then by definition, I write it down by definition, a to the y is x. So you take the base, raise it to the power of y, it gives you x. Remember, we defined the log as the inverse of the exponential. So log is a function that I give it the x at some base. It should give me a y such that the y is the exponent, When I raise the a to the y power, it gives me x, okay? And immediately we can get a very interesting result. If I take a, raise it to the log of x in the base a, it gives me x. And obviously a shouldn't be 1 because 1 to the 0 power is 1, right? And it's not true for that. So basically, yes. So this is a very important property and you can immediately prove it, right? Because again, by definition, log of x in the base a is if it's a number y, then a to the y is x, right? Just substitute, instead of a, substitute log of x in the base a. Log of x in the base a should be equal to a. Should be equal to x, sorry. So basically the idea is that the exponent and the log in the base a, the base and the log in the base a, they just cancel each other out. Sometimes it's easy to remember this this property. So let's have a look at question 19. What is the result of log of 11 in the base 5 in square brackets? And the square brackets means the integer part. Now what is this? So let's have a quick look. What is the integer part of 1.2? It's 1, right? What is the integer part of minus 0.7? It's minus 1. So the integer part of x is defined as a number such that x minus the integer part is always between 0 and 1. So if x is an integer number, its integer part is just itself. But if it's not, you have to make sure that the result of the integer part of x, let's call it fx, such that the x minus the integer part is always a positive number between 0 and 1. Okay, that's why the integer part of minus 0.7 is minus 1 instead of 0. Because if I take the number, the original number, and subtract the integer part, I should get a positive number between 0 and 1. Okay, now this question is interesting. In order to calculate this, first we identify, remember log gives you an exponent, right? So 11 is between which exponents of which powers of 5? Between 5 to the 1 and 5 to the 2. And because 5 is a number greater than 1, the log of 5 is a monotonically increasing function. Remember this plot on the left side? Therefore, if I take the log, then the direction of these inequalities still holds. Log of 11 in the base 5 between 2, and therefore the integer part of log of 11 to the base 5 is 1, right? So the first term is 1. What is the second term? 2 is between 6 to the power 0 and 6 to the what, right? So if I take a log in base 6 and 6 is greater than 1, so log is a monotonically increasing function. Therefore, the direction of the inequalities still remains the same. So 0 is between log of 2 in base 6 between 1. Therefore, the integer part of log of 2 in base 6 is 0. Okay? So this is 0 and the result is 1. Okay? Alright, if 3 to the log of x in base 9 is equal to 2, then what is log of x in base 0.1? Okay, this is interesting. This is very interesting. Let's start with this. Let's call log of x in base 9 y. Okay? So if log of x in base 9 is y, then by definition x is 9 to power y. But 9 is 3 to power 2. So this is 3 to the y to power 2, right? So x is 3 to the 2y. And then we already know that from this definition 3 to the y should be equal to 2. So 3 to the y is equal to 2. So x is 2 to the power of 2, which is 4. So this whole thing was just a trick for you to figure out x is equal to 4. Okay? Alright, then what is log of x or log of 4 in base 0.1 or 10 to the minus 1? Okay. Let's call this z. Therefore x is 0.1 to the power of z, or 10 to the minus z. Okay, if I take the log in base 10, log of x in base 10 is minus z, and therefore z is basically minus log of x in base 10. The reason that I change it to base 10, because I always prefer to work with numbers for base that are greater than 1, because I already know that this function is monotonically increasing. Okay, now if x is 4, 4 is between 10 to the 0 and 10 to the 1. Therefore log of 10 to log of 4 in base 10 is between 0 and 1. But then when I multiply by minus 1, the direction of the inequalities changes. So if I multiply by minus 1, I get z, but the direction is between 0 and minus 1. Okay? If I have a number between 0 and minus 1, its integer part is minus 1. All right? All right, let's have a look at some interesting properties. Log of 1 in any base, and again remember, base is a number greater than 0, is 0. Why? Because by definition any number, any positive number raised to 0 should be 1. This is the definition. This is not something that you can calculate. It's just by definition. Any number to the 0 power is 1. Okay? Log of any number in its base is always 1. And because any number to power 1 is 1, right? Log of x in base a is related to the log of a in base x with an inverse property. Why is that? So it's very interesting. Look at this relation. Log of x in base a times log of a in base x is 1. Why? Let's call the first one y, the second one z. So if log of x in base a is y, by definition x is a to the y. If log of a in base x is z, by definition a is equal x to the z, right? Now substitute for x from the above relation. So a is equal to x. X is just a to the y to the z. But we know this property of the powers, that when you have some power raised to another power, the powers just multiply. So this is a to the y z. Therefore y times z should be 1. We just said that a to the 1 is a, so yz should be 1. Okay, but what was y? Y was log of x in base a, and what was z? Z was log of a in base x. Okay, now the second thing is just an inequality that comes directly from this property. So if log of x in base a is y, log of a in base x is 1 over y. For any real number, y plus 1 over y is always greater than or equal to 2. You can prove this. It's very easy to prove this. And the way you prove it is by realizing that 1 minus 1 over y minus 1 over y to the power of 2, regardless of what y is, obviously y is not 0, should always be greater than 0. This is one of the fundamental properties of real numbers, that any real number to the power of 2 should be greater than or equal to 0. But then you take the advantage of, or maybe a square root of y, assuming that y is positive, okay? And then you take the advantage of the fact that if I square this, it becomes y plus 1 over y minus twice the multiplication, which is 2. Again, this is completely general for any positive number y, and therefore y plus 1 over y should always be greater than or equal to 2. And equality only happens only and if only happens when y is equal to 1 over y. therefore y should be 1, or basically x is equal to a. That's the only way that this inequality becomes 2. Okay, now how many solutions does this equation have? Log of x in base 9 plus log of 9 in base x is equal to 1. I mean, obviously the solution is none. No solution, because if the first one is y, the second one is 1 over y, and y plus 1 over y should always be greater than or equal to 2, or y plus 1 over y less than or equal to negative 2. Again, this was the absolute value or magnitude or modulus of the thing. So if I have something that is the modulus of something is greater than or equal to 2, then if that thing a is positive, a should be greater than or equal to 2. If a is negative, a should be less than or equal to negative 2. Okay, this is just side note. Now this says that y plus 1 over y is 1, so it doesn't satisfy this. 1 is not equal, greater than or equal to 2, and also it doesn't satisfy this one. 1 is not less than or equal to negative 2. All right, change of base. The next property is called change of base. Change of base. Log of x in base a, I can change it to log of x in base b. So I'm changing the base, but then I have to divide by log of a in base b. Basically x and a, they go into the terms of the log in base b. Okay, and one of the interesting thing, or one of the things that we usually write, is write any log with a given base into the natural logs. These are natural logs. Okay, and in order to prove this, we can immediately prove this from the multiplication property. Let's see, log of x in base a times log of a in base b. What is this? Let's call it a, let's call this b. Okay, and let's call the result c. Now if log of x in base a is a, capital A, then let's call them x, some other thing instead of, let's call them u, v, and w. By definition, x is a to the power of u, and for the v, by definition, a is b to the power of v. Therefore you substitute for a here, x is b to the v to the u, and again the powers multiply, b to the v times u. Therefore v times u is log of x in base b. So w is log of a in base log of x in base b. And the way we remember this is that is from this. If base appears in, if a appears in the base and then in the input of the log, they just cancel out and you end up with x and b, x into the base b. Two important things. These are, I'm putting an important on them, is the sum and subtraction, summation. Log of x in base a plus log of y in base a is log of x times y in base a. Okay, log of x in base a minus log of y in base a is log of x divided by divided by y in base a. And again, the proof is very simple. You call this u, you call this v. By definition, x is a to the u, and by definition y is a to the v, and if we divide them, is a to the u divided by a to the v, and the property of powers is that they just subtract, and then you take the log back. So u minus v should be log of x divided by y in base a. Okay, now if log of 19 is a, so just a side note, whenever we don't mention the base, don't mention the base, it's assumed that it's the natural base, or e. e is the base, okay, the natural number. So this is basically ln of 19 is a, and ln is 2 is b. Then what is log of 76 in base 38? That's a little bit complicated. So let's call this x. So 76 is basically 38 to the power of x, okay? First of all, what we know is 30. Obviously, these numbers have to have some sort of relation between 19 and 2. Otherwise, it's really not easy to write them in terms of the a and b. So 38 is 2 times 19, okay? And we know that 19 is e to the power of a, and 2 is e to the power of b, okay? So what is 76? Let's see, 76 is 48 times 2. No, sorry, 38 times 2. And 38 is 19 times 2. So this is 2 to the power 2 times 19, okay? So 2 to the power 2 times 19 is equal to the 38 2 to the 19 times power of x, okay? So 2 to the x minus 2 is equal to the 19 1 minus x, okay? Now what do we understand from this is that again, we can substitute the definition of a and b. So 2 is e to the b. I'm going to write it maybe here in this corner, or maybe let's just continue here. 2 is e to the b times x minus 2 is equal 19 e to the a 1 minus x, and the bases are the same, so the powers should be equal. B times x minus 2, a times 1 minus x, okay? So a plus bx is equal to a plus 2b, therefore x is a plus 2b divided by a plus b. The first choice.